Okay. All right, everyone. Welcome to the Robotics Colloquium. We meet most Fridays and have distinguished speakers. And today it's a real pleasure to introduce Terry Fong. Known Terry for a long time. Terry is the chief roboticist at NASA Ames. Has been there for a bit. And has been leading a lot of the technical and academic work, as well as like putting it out there on like actual real robots that leave planet Earth, which is incredibly important. Um, we've interacted both like as peers, but also through NASA has a really wonderful PhD fellowship program, and I've had students who have participated through that. So if students are out there and are interested in talking to Terry about that, please talk to him. I do have like an anecdote about Terry that I do want to share. I started my PhD at Carnegie Mellon in 1999, very long time ago. And one of the star students there was Terry Fong. And Terry's PhD defense was one of the first thesis defenses that I attended. There was a little kid sitting in the back, but it was incredibly impressive. I think what really impressed me about Terry, and it was very motivational for me too, because it was just this ability to connect something that is incredibly practical and pragmatic with something that is incredibly theoretical and algorithmic, and actually put things out there in the world that that are out there really interacting with complicated environments. And there's no more complicated environment than like being out there in space or on the moon. So without further ado, Terry.
Great. Thanks very much, Sid, for that glowing introduction. I don't even remember any details from my thesis defense other than being up there in front of the committee, some of whom I only met that day and being terrified. So in any case, I don't remember all the details of who was there. That's amazing you were actually in the audience. But having said that, it is my great pleasure to be here at UW. I have to admit something that I've been embarrassed about for many years, which is that my wife is a native Seattleite. My mother-in-law still lives 2 miles from campus. I got married in Seattle more than 30 years ago, and today is the first time that I've ever set foot on this campus. Okay, so I have driven up and down, on Sandpoint, I mean, literally thousands of times, and like, oh, hey, look, it's Husky Stadium. Oh, look, there's a campus, but I've never set foot. So I am so glad to be here today. Apologize for not getting here sooner, but I'm here now. In any case, today I'm going to spend maybe the next 40-ish minutes or so talking about what I've been working on for the past several years. It's a mission called Viper that NASA is now planning to launch next year, actually in August of 2027. It's something we've been working on as a priority for supporting not just a better scientific understanding of the moon, but also future human exploration. And I'll talk about why that's all important in a minute here. Over the next 40 minutes or so, if you have questions, feel free to raise your hand. I'll try my best to try to answer them during this talk here, but obviously there's a bunch of slides we would like to try to get through, and hopefully we can. And I'll try to save maybe a little time at the end for some additional questions. So to start with, 2 decades ago, the moon was considered a very different place than it is today. We had, of course, studied the moon from orbital observations. Obviously, samples returned during the Apollo missions. And the general thinking up until about 20 years ago was, oh, yeah, the surface of the moon is a bunch of rocks. It's really dry. It's really bone dry. And maybe there's a thin exosphere of a few elements here. But fundamentally, we thought, yeah, we've sampled it. Yeah, nothing interesting. It's a basically ball of rock in the sky. But that changed with a number of missions, including a couple of missions that NASA conducted, including one called LCROSS, which was an impactor. Which took a look at the fact that the moon is more than just a bone dry place in the sky, and that in particular it's a place where there are volatiles, or in particular perhaps water ice. And water ice that is permanent on the moon, that is it's on the moon in a condition and in locations where it can actually be sustained over billions of years. And that's actually groundbreaking. The idea that there might be volatiles there means that there are resources to potentially be had. If you think about trying to sustain life, the things you need, of course, are things like hydrogen and oxygen because you can create water. But those also happen to be the 2 most important things you need to make rocket fuel. So instead of having to launch everything from Earth, if you could take advantage of in situ resources, that is volatiles or hydrogen in particular, on the moon, hey, this changes everything. Now the moon is the greatest gas station in the sky. It's a place where it's really important to go to because you can use that as a launching point for anything else you care to do in either the Earth-Moon system, cislunar space, or beyond. And because of that, there's been a lot of focus on trying to understand where exactly is there water ice, and in particular at the lunar poles. And is this water ice in certain locations? That is it at the surface? Is it the near subsurface? Is it deep underground? Is it stable in areas where temperatures are within a certain range? And one question of that is, well, what does that actually mean to be in a certain range of stability? There's an interesting thing called permanently shadowed regions on the moon that we've identified. They're locations that never see sunlight. And therefore, they're probably the coldest places within the solar system. Places, especially at high latitudes, where the topography is such and the incident of sunlight from the sun just will not get into these deep craters. And the craters actually don't necessarily need to be deep or large. There can be permanently shadowed areas that are very small scales, even sort of like millimeter, centimeter scale, not particularly of interest if you're trying to get bulk resources, but other ones that might range up to tens of kilometers in scale. And so, of course, the question is, if ice really does exist in these places, especially in permanently shadowed regions, can we identify those locations? Can we map them and understand the extent of these deposits? Can we understand the composition of these volatiles? Are they basically in the few percent by weight within soils that is mixed into the soil matrix? Or do they exist in larger sort of bulk concentrations? These are things that we don't know today because in order to find those out, you have to be on the surface. You actually have to sample these materials. You can't just observe from orbit. You need ground truth. And that's led NASA to propose many years ago a mission to go do that, and that's called VIPER.
The future of human space exploration is being driven by what we can discover and accomplish on the moon. And with NASA's confirmation of ice existing at the lunar South Pole, the critical task of finding and mapping where water exists, what form it is in, and where it came from can now begin. Leading us on that journey will be NASA's first mobile robotic mission on the moon, known as VIPER, the Volatiles Investigating Polar Exploration Rover. It will be delivered to the Nobile region of the South Pole as part of NASA's Commercial Lunar Payload Services Initiative. This region sits just outside the western rim of Nobile crater and covers an area of 36 square miles. As the first ever resource mapping mission on the surface of another celestial body, VIPER will roam the surface equipped with 3 science instruments and a drill to detect and analyze various lunar soil environments at a range of depths and temperatures. The rover will venture into permanently shadowed craters, some of the coldest spots in the solar system, where ice reserves have been preserved for billions of years. NASA had 4 critical parameters when choosing a landing site for VIPER: available sunlight, Earth visibility for communications from the moon to the Earth, data showing the potential presence of water and other resources, and terrain that is well suited for VIPER to navigate. The area to the west of Nobile crater met these conditions. Once on the surface, VIPER's mission will last 100 days and cover between 10 to 15 miles. And while a baseline traverse route through the Nobile region has been identified for the rover, the scientific discoveries VIPER makes along the way will actually influence where the mission team sends it next, so its planned route will most likely change. During its travels, VIPER will visit at least 6 locations where data suggests ice could be found. By helping determine the locations of where water and other resources exist, VIPER's findings will help pave the way for future landing sites under NASA's Artemis program. The prospects of achieving a long-term human presence on our moon never looked so bright.
So VIPER as a mission has 2 primary science objectives. One is to characterize the distribution, that's both sort of horizontal and vertical, of volatiles, including the physical state. And then the second is to evaluate the potential. That is, is it possible to make use of these resources for what's called in situ resource utilization, or ISRU. There are many challenges with going to the moon. The moon is actually a much more difficult place for robotic missions than Mars because of the conditions such as dynamic lighting. This is in the polar regions, which means that we have the sun at very low angles above the horizon. That results in very long cast shadows and dynamic shadows. They move up to a couple centimeters per second, which for a very slow moving robot, which all space robots are, is terrifying, especially if you're solar powered. There's also this interesting challenge of this being a mission of prospecting versus going to, say, fundamentally be a sampling mission where you can spend a long time planning where to go and sample. Here, our primary goal is to be prospecting all the time, which translates into things such as we care about the average rate of progress or the speed made good moving from point to point. It's a challenging mission also because this will be a fully interactive one with a mission control team working in real time directly with the robot. That's something that we don't do for Mars. And Mars, because of time delay and because of the fact that the rovers are long-lived, years versus hundreds of days, it really drives home a high cadence set of mission operations structure and the way the team thinks about working with the robot. The robot really is an extension of the scientists and engineers behind it on Earth, but it's something that's going to be short-lived, 100 days, and have to be really driven as efficiently as possible. Yes?
Why is this mission going to only be 100 days instead of like Mars, say, where you make it last for years?
Great question. The first part of the answer is it's a solar-powered robot, which means we are limited by being able to get adequate exposure to solar illumination to maintain charge. And there's a battery on board, but we can only store so much power. The second part is because of the way the moon is, that we are always going to have this contrast between lunar day and lunar night. In equatorial regions, lunar night and day and night are pretty evenly split, like 2 weeks each, which means if you want to basically have a robot that can survive, it needs to be able to survive lunar night, which if you think about the lack of sunlight means, hey, survive in like 40 Kelvin temperatures. Incredibly difficult to do. For Viper, we are somewhat fortunate in the fact that we're going to the polar regions, which tend to be higher elevations, and we have identified locations that only experience short duration nights, like 4 or 5 days in duration. Great. So identify these safe havens, go there, and if you can survive with a battery powering survival heaters, you can survive any number of these nights as long as you can go to these regions. Unfortunately, we can't identify more than like 4 or 5 or 6 of these in a row, and we can string those together. That gets it about 100 days. Kind of complicated, long answer, but that's what's going on here. Yes?
Question. You said that the rovers move kind of slow.
Yep.
Is it because they're solar powered and they kind of want to conserve battery, or is there a different reason as well?
There are a couple of reasons. One is, yes, when you design a space robot, it's really a system engineering problem. You're limited by mass, you're limited by volume. This is a solar powered rover, which drives a limited power budget overall, a few hundred watts total power. But you're also limited by what you're carrying in terms of your instrumentation. So in particular, there's one instrument that we rely upon for prospecting that's a neutron spectrometer. It doesn't operate fast. You'd like to drive at no more than, say, 20 centimeters per second as it's making measurements of basically hydrogen in the near subsurface. Okay. As I said,
Can you talk a little bit about
yes.
the history? I saw the last, it seemed very interesting.
history. Yes, I didn't get to the history part here. I was hoping to skip over that. So Viper was not the first mission that NASA was interested in doing this kind of prospecting for volatiles. From the period of 2014 to 2018, there was a mission called Resource Prospector, which was in development. All this work has been led by NASA Ames with work at NASA Johnson and NASA Kennedy. But Resource Prospector went through what's called Phase A and Phase B, which led up to preliminary design, and then it was canceled for a variety of reasons in 2018. It reemerged shortly afterwards as Viper, and that went into 2024, at which point, for other reasons, having to do with budget, and frankly, budget was directly linked to the pandemic in terms of what that did to overall supply chains and delays and everything. Just an example, the camera systems for Viper were commercial cameras that were 24 months late. Okay, so if you're an engineering team and say, oh, hey, my cameras, I need it on this date here so I can do integration, and this date so I can do testing, and then you're told, hey, you gotta wait 2 extra years, that just completely messes up your schedule. And as a manager, what does that mean? Well, if it's delayed, I have to keep those people on, or I have to bring them back, or if I can't keep them and I can't bring them back, I have to hire new people. That tends to cause only bad things to go wrong with budget. Anyway, for all those reasons, and I'll show you where we ended up in 2024, the Viper mission was canceled, and NASA said, well, look, we're so close to launching this system, let's figure out what to do. And fortunately, in September, NASA figured out, okay, here's a new way to actually approach this here. We'll go ahead and we'll basically resurrect Viper. We won't change the name, it's still Viper, and it's actually gonna fly now. Okay. In terms of mission overall specs here, as I was saying earlier in answer to the question about why doesn't it last years, we're looking at 5 to 6 lunar days, so maybe about 100 days on the surface of operations, depending on what the final traverse works out to be. Trying to get about a 20 kilometer total traverse distance with potential up to 30 kilometers. The system's designed to be able to drive 30 kilometers. And by the way, this is really fast compared to what we've done on Mars in terms of distance per unit time. Operating in temperature regimes that go from 40K to 300K, carrying out up to 50 1-meter drilling activities, and lots of interesting things about this mission that are quite different than other missions. Alma.
Good to see you. So I had a general question,
Yep.
which may be of interest. So, will there be future interest in the equatorial regions of the moon?
Yes.
Deploying rovers there?
Yes, and in fact, NASA is interested in sending robots to lots of different places of the moon. Obviously, the polar region is of great interest because of the potential for in situ resources. But there's obviously lots of things that we still don't know about other parts of the moon. So not quite equatorial, but there's, for example, these areas called lunar swirls, which are these magnetic anomalies. We don't understand why do we see these strange behavior of magnetic fields. And so there's actually a mission called Lunar Vertex that targets that. And that's supposed to also launch, I think, in 27 to go take a look at that. As the video said, the mission area we're going to is a place called Nobile, at least on the western edge of Nobile crater. That whole general region has since been renamed, or maybe not renamed, it has been named as Mont Mouton after a NASA mathematician who used to work at the Goddard Space Center. The flight rover itself looks like this today. The final assembly was completed in June of 2024, so this summer it will have been 2 years since we finished building the flight system. This is actually shown in a clean room at NASA Johnson, where we did all of our integration. And you might ask, well, why was it integrated at NASA Johnson? And one reason is because it's a large system, and we wanted to take advantage of the environmental test facilities that exist at NASA Johnson. So one of those is a large test chamber called Chamber A, NASA being very creative in naming. It's a very large place we can do thermal vacuum testing. And so we basically assembled the rover there, and it was a short distance from one building to another to basically do testing. But the rover is fully assembled. It has been assembled, ready to launch since 2024. Since there are a lot of robotics people here, just to tell you about this, a fully electric powered rover has solar arrays on 3 sides. It has a total of 8 camera systems, including a pair of stereo cameras on a pan-tilt unit on the mast. We use that for primary navigation. There's a comm system involving a high gain and low gain antenna that's also on a pan-tilt system for direct line of sight to Earth. There are other cameras such as aft stereo cameras. There are cameras in each wheel well to look at the wheel-soil interface. There are 3 instruments on here, 3 primary instruments, 3 spectrometers, a neutron spectrometer, near-IR spectrometer, and a mass spec, and a 1-meter rotary percussive drill. All of those things come together as the full surface segment that is basically the thing that moves on the surface of Viper. Viper, just in comparison to some of the other systems you can see here, it measures with a footprint about 1.5 by 1.5 by 2 meters in terms of the sort of outer mold line, 430-ish kilograms or so, top speed 20 centimeters per second. And you can see how that compares to, for example, on the top row, a bunch of Mars systems, and on the bottom row, lunar systems here. So solar-powered, fully electric rover. I'm often asked questions like, well, why isn't it powered by radioisotopes so you wouldn't be dependent upon being able to stay alive? And the answer was that when Viper was started, NASA said, look, we want this mission to go quickly, and the one way to ensure that your system will not go quickly is to integrate anything that's nuclear, because that requires a ton more testing, a ton more paperwork, access to very limited supplies of radioisotopes, and all that kind of thing. So we avoided that. In hindsight, now that we've known how long it's taken, would we have maybe reconsidered? Maybe. But as it is, we're a fully eco-friendly, fully electric, solar-powered rover. Yes?
So for the electronics inside the rover, like, do those have to be like spec'd up to withstand like radiation, or like can you now use like more consumer-grade electronics?
Yeah. So there's two sides of the answer to that question. One is that we, of course, are trying to make this system be as risk tolerant as possible. That is, so we recognize, yeah, radiation hits, especially upsets or even, full latch up, are issues. And so for the avionics, at least in terms of computing, we kind of tried to split the difference. So there are actually two main computers on board, one of which is a radiation-hardened, really robust, bulletproof system that's flown on many missions. The processor, if you're interested, is a RAD 750, so it's a radiation-hardened processor, but it's incredibly slow, super slow. I mean, everybody here has something that's easily 10 times faster in your pocket, maybe 100 times faster. We also have a radiation-tolerant processor that we use to do some onboard image processing. It's not consumer grade. It's like a 1 gigahertz, I think 8-core processor. It's tolerant. So if it gets hit by a particular bit of radiation, it will likely reset, but it's not the sort of core function. Oops, and I don't know why it wants me to log onto the network. Yes?
So to that question, is it, like, how difficult is it for you to, like, say, take commercial grade compute stuff and put it in a box that is radiation hardened so that you could leverage the compute that we now have access to without needing to worry too much about the radiation?
Yeah, that gets into questions of how does that fit into the overall system engineering thing? Because if the box is very heavy, that's a problem because you're adding mass that is only to make sure that the electronics work. Or if there are thermal considerations, like, okay, now you've enclosed stuff in a nice box. Well, what if it gets too hot? How do you get rid of the excess heat? These are kind of engineering trades for all space systems you have to deal with. And so even though you could say, hey, we could simplify so much if we use faster commercial grade computing, that's fine until the thermal engineer says, well, no, you're screwed up my life. Okay. Let me move on here. I'll skip past the instruments because I briefly mentioned those earlier and skip past some of these things here to talk about some of the more interesting robotic things. This is a 4-wheel rover as independent steering, suspension, and propulsion, that is rotary drive. That's different from the rovers on Mars, which have up till now been 6-wheel rocker bogie systems. We did this to get greater capability from the rover, and that is that we wanted a system that could deal with environments where we knew less about the environment. There's very little that's known about the surface composition in permanently shadowed areas. The scientists that we've been working with, the lunar scientists say, oh, permanently shadowed regions likely have fluffy soil. And I said, well, fluffy is not a very precise term. Can you define it? No, we can't because we don't understand the actual distribution. What's the compaction? How unconsolidated is the material? And so we chose to go with a system where we could control suspension. That gives us the ability to do things like not just drive in a normal manner, which is basically explicit steer, but we can do other things like we can wheel walk. We also use this to be able to level the body to make it easier to ensure that the drill penetrates normal to the surface. And of course, we get that through controlled actuation. To give you an idea, this is just a video of functionally checking out the vehicle. You can see how it can basically roll in terms of primary locomotion. We can steer. We also have the ability to control suspension here. And of course, every single one of these 12 degrees of freedoms is independently controlled. I'm sorry, I'm going to have to break out of this for a second. My network keeps trying to connect. We've done a lot of testing with the overall wheels. We've tested out to 40-kilometer drive, which is 2 times the target baseline range here, driving routinely over a variety of different rocks in different configurations. This is some testing that was carried out in Pittsburgh at a small company called Proto Innovations. just giving you an idea of what it means to do testing of planetary rover wheels. And this is sort of an endless back and forth driving and doing lots of recording and assessment of the wheel. And on the outside of the wheels, we have grousers, basically these ridged sheet metal fins that we use to go over things. We've done a lot of testing in places like the Slope Lab at NASA Glenn, which is a place that has this large bed that we can raise and lower at different inclinations. And we have lunar soil simulants, or simulated lunar soils, that we can do testing of things like rock traversal. Actually, this is kind of interesting. We made a smart rock here by putting a load cell on a rock to kind of measure the forces that are experienced by the rock as a way of trying to really better understand the overall forces involved with going over and around rocks. Testing in large situations like craters, which are the same scale as the rover. Trying to look at how much snow plowing you're going to do if you go into very, very loose material. For here, it's like a rover-sized crater on a I think 15-degree slope. Extremes of slip testing. So this is like 30-degree slope. This is beyond anything that we would expect to drive in, but just in case we're trying to understand the overall capabilities of the system. And that also has led to some interesting innovations that Viper has done. This is work performed also with Proto Innovations in Pittsburgh in terms of like real-time slip detection, making use of inertial measurements, motor current, and wheel odometry to basically assess in real time how much slip is occurring, how much loss of traction is occurring, something that has not been done to date for planetary rovers. And this feeds into our onboard hazard detection system in order to control the way the robot moves across the terrain. We've also tried to look at the worst case scenarios. So as I said, we've been hearing from the lunar scientists that permanently shadow regions are fluffy, which means, of course, they're great places to get stuck. In order to test that, one of the things at NASA Glenn is this, which is called the sink tank. This is actually filled with phyllite. If you're not familiar with phyllite, these are basically these very small ceramic beads. They're spherical. If you ever have kids or seen kids playing, those bins with lots of plastic balls and just kind of laugh at them falling down all the time, well, that's the kind of thing, except at a much smaller, finer scale. It's the worst possible thing for a wheeled locomotion system to try to drive through. And we've done testing to verify that we could actually get through that. The way we do that is through the use of these alternate mobility modes. So this is our ability to control suspension, steering, and rolling propulsion in interesting ways. So this is an inchworming gate. So the rover doesn't just drive normally, but it actually, takes advantage of all these three different degrees of freedom on each wheel well to control its behavior. This is a wheel walking kind of behavior. And we've looked at all kinds of gates, ones that look more like walking, ones that look more like swimming, ones that are hybrid, as a way to understand what's possible if we get into a really bad situation. So a really kind of unique thing that you don't see with other planetary rovers. Another thing that we've been doing is to take a look at how can we routinely move while tracking the Earth, because the operation for Viper depends on real-time communications, line of sight, point to point from the rover to Earth. And so here what you see here is a view of a camera that's placed at the location of the high gain antenna. It's looking at the moon, and we're driving outside at nighttime and verify that we can maintain pointing at the moon while moving. So as the robot's going over rocks and through craters, it has to be able to adequately track and make sure the moon stays within like a 3-degree pattern here. Another part of this mission, of course, has to do with how do we operate the robot? How do we navigate in terms of localize and identify hazards? So one part of that is an extreme reliance on the use of camera systems. There are no rover qualified appropriate scale LiDAR. Even now, there's a lot in development, but by and large, planetary rovers rely upon cameras, and in particular stereo vision. Because we're going to dark areas, we also have to make use of supplemental lighting. So Viper will be the first planetary rover with essentially headlights. And we did a lot of testing in one of the labs at NASA Ames called the Lunar Lab. Really creative name again. It's a place where we have a high fidelity representation of the lunar surface. And we do that by taking 12 tons of one of these lunar soil simulants called LHS-1, which actually stands for Lunar Highland Simulant, also a very creative name, in a large sandbox that we have created scaled representations of representative lunar terrain. So, for example, we have size frequency distributions of craters and rocks for the moon of the area we're going to, so we scale that down, put that into the sandbox, and they're actually created by hand. It's kind of a thankless task, and I will admit that interns spent a lot of time basically handcrafting these terrains, and not just a single terrain. We wanted a variety of terrains for test purposes. We have lots of data sets. If you're interested in actually taking a look at these things, there are a number of data sets that we've released publicly from this testbed already, and we'll continue to do so. And we use this kind of testbed to basically check out computer vision systems and camera performance and light performance, at least in a scaled setting. That leads to the next interesting thing, which is mission planning. Viper, as a mission that has to operate over a short period of time, relies very heavily on the effectiveness of mission planning. And because it's a mission of discovery, everything we learn about the lunar surface and lunar subsurface as we go changes the way we think about the rest of the mission. So replanning continuously is a big part of Viper. We've relied very heavily on a number of methods to do that, to come up with strategic and tactical plans. But we have to do that in the face of constraints such as the distribution and state of lunar volatiles. What have we observed so far? What are constraints such as line of sight communication to Earth, the total drive distance thus far, what's the distribution of slopes, driving speed, the fact that we're worried about moving shadows up to about 2 centimeters per second. That causes us to have to come up with systems that can do everything from automated analysis of plans that take into consideration these constraints, and we make use of high-resolution 3D terrain models that we've created to generate strategic traverses that we then feed into tactical traverse planning. And that produces, at the end of the day, things like this. So this is a typical Viper traverse. The arrow represents where the rover is going over time. This is a traverse plan if we had been operating from like November 2023 out to March of 2024. You can see the rover basically staying in sunlight. Sometimes it gets to locations where it has to wait for the sun and shadows to move in an appropriate manner so that as it starts moving again, it can actually get to the next location. Sometimes you have to be at a certain location on time, that is a safe haven location, in order for you to stop and survive a lunar night. These are the kind of plans that we typically roll out hundreds or thousands of possible traverses and then evaluate them for fitness to come up with suitable, basically X, Y, and time traverse plans. The kind of thing you just cannot do in a manual way. Another interesting thing that we've done to basically test our systems as well as to support mission training is development of high resolution, high accuracy, high quality simulation. So there's a simulation system called the Viper Rover Sim, or RSIM for short, that we've developed to focus on high quality lunar lighting simulation, high fidelity camera modeling, real-time slip modeling, and the use of very, very high resolution synthetic lunar terrain models that are still scientifically plausible. What this means is that we will use our lunar lab to test cameras, and then we'll try to recreate that in simulation for things like camera modes. We worry about what is the performance in simulation versus the real world of, for example, exposure. We worry about other camera parameters such as lens flare, and you can kind of look at the comparison between the lab and the simulated versions, or other things like fixed pattern noise or flat field effects on the imager, or even depth of field. So we have very, very, very precise camera models that are used in simulation to help us support things like development of the navigation system, which uses, for example, stereo vision to generate point clouds that we then register against DEMs to come up with position estimates. One part of that has to do with creating digital elevation models. We have a set of tools called the AIM Stereo Pipeline. This is basically open source photogrammetry tools. This is one of the DEMs that we created using an instrument on the Lunar Reconnaissance Orbiter called LOLA. That's a laser altimeter. You end up with these DEMs that are like 5 meters per pixel. And these are considered like the gold standard of, sort of like the base coordinate system for the moon, the laser altimeter readings. But of course, this is at a scale that's useless for rovers. 5 meters per pixel, you have a rover that's 1.5 by 1.5 meters. It's just lost in a single pixel. So instead, what we do is we build higher resolution models. This is using a photocalorimetry technique with the stereo images that we get from the Lunar Reconnaissance Orbiter to come up with 1 meter per pixel. But even this is not sufficient if you're worrying about testing your computer vision systems or doing training. And so instead, what we've done is we've taken that as a starting point, and then with these size frequency distributions of things like craters, come up with synthetic terrains that are scientifically plausible. So as an example, which is really dim to see here, this is a 1 meter per pixel actual lunar DEM. We'll apply our knowledge of the craters and rocks to come up with higher resolution synthetic terrain. So this is a 4 centimeter per pixel version. And then that results in our ability to do surface simulations like this, which I know is hard to see on this screen here. I think the YouTube stream later on will have a better version of this here. But this is basically showing us with a very high photorealistic fidelity simulation of the lunar surface, including cast shadows, and this interesting effect called the opposition effect, where if you look directly down sun with the camera, everything that's zero phase, that's directly in line, looks artificially brighter than the rest. It has to do with the way the lunar soil grains reflect and collimate light. Another interesting thing about VIPER has to do with mission operations. As I said, we are thinking about this as an interactive mission with the ground control team working in real time with the robot on the moon. And to do that, we have a number of key points of the way we do operations. There's the engineering function, which is basically how do you understand where the rover is, how do you command where it goes. There's coupled with the real-time science aspect, which is how do you take a look at the data that comes back from the mission, from the rover, and then do planning of the next places to acquire additional surface measurements. The way we do that is to use a distributed operations team with the bulk of people at NASA Ames down in California, supported by people at NASA Johnson in Houston and people at NASA Kennedy in Florida. We operate driving basically from science station to science station, and the goal going between science stations is to get from science station 1 to science station 2 as rapidly as possible. That leads to all kinds of interesting things. If you're an AHRI person or a human team person, the challenges of figuring out how do you construct an operations team is really fascinating. And to do this, we took a look at the way that Mars rovers have been operated to date. We looked at the way that the robotics on the space station have been operated to date. And we tried to figure out where is the intersection with those things, plus the kinds of things we were worrying about for VIPER. And you end up seeing that VIPER as a system, shown in purple here, ends up with things that share aspects of either Mars or ISS, but is still uniquely different. So for example, we rely upon the idea of command sequencing. We command the rovers not in terms of like real-time joysticking, but we send commands in terms of like position, move from this waypoint to another waypoint. That's just the same way that Mars rovers operate. But we also have to deal with extreme lighting that you do not see on Mars, but you do see on the space station, because the space station orbits the Earth. It goes from light to dark periods very rapidly, and that's similar to the kind of things we worry about for VIPER. As part of real-time science operations, we have a science team that works very closely with the operational engineering team. They make interactive decisions about where to go based on the data that's been collected to date. And there's been a lot of work here that actually derives, I think, a lot of approaches and organizational techniques from the way that here on Earth we do like marine science. If you've ever been involved with people that go out in the ocean on board research vessels, oftentimes you'll rely upon like ROVs that are deployed from the from the ship, and you have real-time operations teams, real-time science teams working with that ROV to conduct science. VIPER's science operations is very, very similar to that. They use tools to look at real-time plots of information. They generate real-time plans. Part of what we do is making use of a system called OpenMCT. It's NASA open source as an open mission control set of tools. Also, we make heavy use of MAP. As you might guess, this is fundamentally a mapping mission. There's a set of tools that provide real-time geospatial data for the science team. And then, as a roboticist, the thing I, of course, care about is not just the science, but it's really thinking about how do we operate the robot. And to do that, we've focused a lot of thought about how do you effectively operate a robot that has to make as much progress over time, moving from point to point. Within the Ames Mission Control Center, in particular, the front row of the operators here is what we consider to be the drive team. That's a collection of people, including a real-time scientist working with the driver and a co-driver and a navigator to effectively try to figure out where the robot is, how to turn it, figure out where it needs to go next, and then command and monitor its execution along the way. This team has to worry about the idea that there's a command cycle, like I said earlier, like Mars, where you're basically trying to do things like terrain hazard assessment, motion planning, image planning, interactive science, and commanding waypoints in an interdependent team manner. But you're doing this over and over and over again. generally in the order of like 4 to 5 minutes per command cycle. So that translates into making basically, 10 to 15 mission critical decisions an hour continuously. It's a real challenging thing to do, and we spent a long time trying to conduct operational simulations to validate the overall approach for doing this. The main motion control thing that we focus on, of course, is waypoint driving, and at the speeds we're operating, this means basically commanding the rover 10 to 15 times an hour to drive 4 to 8 meters per waypoint from its location. And then the rover, of course, has to basically execute this on board and be able to move from point to point in an efficient and accurate manner. I'll just point out that this is just a snapshot of the kind of tasks that are done continuously by this ops team. Everything from assessing the robot's state and terrain hazards to planning tactical paths, thinking about rover motion, and keeping in mind that we have the ability to control steering, rolling, and suspension behavior, all from at the same time by this team, planning for navigation imaging and doing all this commanding. But this looks complex unless you break it down and think about it as a roboticist and think, well, that basically means we're doing the same thing as all robots do. We're sensing, we're planning, we're acting. We're just trying to do this with this kind of hybrid system where the robot is carrying out some portion of this, the humans are carrying out some portion, and the humans are supported by decision support tools to help make this possible. Now, to answer any question that might jump up here, why isn't this done all autonomously on board? And that was because Viper at the mission start was conceived to be something that would have to fly very quickly, within like 3 years. We didn't have time to carry out a full detailed test campaign where we would actually test all aspects of the onboard autonomy. But we built all the tools for doing that. It's actually, from a robotics point of view, very easy to go from the support tools that we provide operators to say, oh, we'll just put this all on board, we'll close the loop. But we haven't because of the driver to get this flown quickly. I'll just try to wrap up in the next few minutes here and show you that this is one of the operation tools. It's the primary rover driving interface, a system called Verve, where we take a look at camera images. We have digital elevation models and this 3D view that's based on orbital data. That is data we have now today that's acquired about the moon. But again, that's only at about 1 meter per pixel. We end up with real-time assessments. So we take stereo images on board the rover to build hazard maps. And those are constructed based on our understanding of the capability of the rover for handling like step obstacles, positive, negative obstacles, or slopes. And we then color code that and provide it to users to make real-time decisions with that. So this is how this works. This is real time. So the operator will place a waypoint, and you can see a ghost rover indicating the overall pose of the rover. We'll control things like the orientation relative to the current waypoint. There's a kind of like target over in the top left. That's the location of the navigation imagers. And we worry also about making sure that we have coverage from waypoint to waypoint to support things like visual odometry. So we want to make sure there's sufficient overlap between images. We can also take a look at prior data. So here is like a past NavCam image that basically the operator is flying into to do fine adjustments here. So you can actually see the image overlaid upon the 3D terrain. And then we'll just go ahead and command the rover to drive. And of course, after some delay, which is on the order of about like 10 seconds in general round trip latency, having to do with the fact that we have to communicate through the deep space network. So there's ground station buffering and all that. Then the rover will start driving. In this case, it's driving in this the rover simulator, but all this would work the same way when we're on the moon, hopefully next year. And that takes me to the last couple slides, which is the Viper flight mission. As I said, in September, the decision was made to move forward with Viper, and there was a public announcement that NASA would work with Blue Origin. So just down the road from you all here to get to the moon, and that's actually the reason why I'm in town, is for a meeting next week with Blue Origin. Blue is proposing, or planning, I should say, not proposing, is planning to carry Viper to the moon on their Mark 1 lander, which is actually the largest lunar lander ever built to date. This is an 8-meter tall lander, and the rover's going to land on the moon at the top, 8 meters high. So, of course, there's a big challenge of how do you get from 8 meters above the ground to the ground? You don't just roll off or jump off. And so there's a lot of work now on sort of crane-based systems to try to safely offload the rover from the top deck of the lander to the surface. This lander is designed for Blue Origin's New Glenn launch vehicle, which has a 7-meter diameter fairing. That is the place where you can put all this whole stack in. So it's a really large system, and also has great, I think, sort of mass capabilities for things far beyond Viper. Where we are right now is that it was announced back in September that we were moving forward together working with Blue Origin. Blue Origin's base contract period goes through this June, where they're basically designing the accommodations. That is, how will the rover be carried on board their lander, demonstrating how to get it off from the lander, and then that leads to the option period, which we fully expect will carry on beyond June, all the way to the launch of Viper in August of 2027. In between that time, Blue Origin is launching their first version, or the first unit of this lander, serial number 1, which will launch later this year, and then serial number 2 will carry Viper in August 2027. Our expectation is that by the time we land in September 27, that will set us up for about 4-ish months of operations on the lunar surface. And then we'll cease surface operations in January. And by the time we finish with data analysis, and a lot of the data from Viper is going to show up in the planetary data system, which is this public database of past NASA mission data, it'll probably be around the end of September 2028. But I'll end there. I think we have 5 minutes left for questions. I'm happy to talk more about anything that you heard but didn't get to ask questions about. And if you're interested to learn more, there's, of course, a web page. And I'm probably one of the easiest people at NASA to find anywhere, so just send me email. Yes?
I think in one of the earlier slides, you mentioned, you were talking about the components on the robot. One of them was a star tracker.
Yes.
I think I know about them, but I think they're very interesting. One question I have is, do you have like the equivalent of GPS around the moon? If so, why use a star tracker? If not, then it's kind of obvious why you use a star tracker. And then for others, I'd also appreciate it if you could explain star trackers. I find them very interesting.
Yeah, so Viper carries a star tracker, which basically has a map internal to it of the stars, and it makes observations of the sky to figure out, in particular, overall orientation relative to the star pattern, or to the star field, I should say. We use that for Viper for our way to estimate absolute orientation. We, of course, can do better than that at higher rates with the inertial measurement unit we have on board, which has a gyro and accelerometers. But for absolute, especially orientation, we rely upon the star tracker. And in answer to your question, no, there is not the equivalent of GPS today at the moon. There have been discussions about can we set up a temporary or maybe longer term, maybe not permanent, but over some period of time, sort of equivalent to GPS. Doesn't exist yet. Yes?
Is this the first teleoperated mission to be held from Earth, or there have been some previous work done on teleoperations?
So, in terms of planetary rovers, obviously for NASA, our prior rover missions have been to Mars. And the round trip communications delay, which can be up to 40 minutes, prevents us from operating in an interactive manner. I hesitate to say that Viper is purely teleoperated because it obviously still drives itself from point to point. And in fact, it has onboard safeguarding to avoid like slip situations, or in the case of loss of communication signal, it knows enough to try to back up and try to reacquire the communications at like the last known good location. So if it gets blocked, for example, by some terrain feature because the rover slipped and all of a sudden it dipped down, it's going to try to back itself up and reacquire signal. There, of course, have been other planetary rover missions. China has had missions on the moon. And of course, that means that we, people on Earth, have acquired some data from lunar robots. But this will be the first NASA robotic mission, a surface robotic mission to the moon. Yes?
This might be a lengthy question, but you mentioned that like the path that the rover will take once it lands is like somewhat predetermined, but willing to change.
Yes.
And I was wondering, I think the rover mission on Mars, they don't analyze the samples on the moon or Mars itself. So, other than like the checkpoints that you guys establish, what will influence the change in path? Would it be environment issues, or would it be like you can't analyze the checkpoints themselves, right?
So one of the things about Viper is that the instruments provide real-time telemetry. So we can analyze it in real time. And the science measurement plan for Viper has to do with the fact that we've basically treated the moon as representing 4 distinct ice stability regions. So based on, is ice stable on the surface? Is it stable at the nearest subsurface, down to maybe like 50 centimeters? Or is it stable below that? And of course, then there's the area where we don't expect to see any ice, so it's the dry sort of control region. In each of these regions, the primary goal is to accrue a certain amount of measurements over unit distance and spatial coverage. And so in real time, the science team is saying, hey, we've got a lot of data in like the near surface area, but not so much in the deep area. And that will dictate how do we then reprioritize traverse planning to say, okay, let's try to get more deep measurements. The other factor is that we can't see every sort of obstacle from orbit, which means that even though we plan out traverses which look like they go over totally benign areas, maybe it turns out there's actually a lot of like 20 centimeter rocks which just prevent us from moving quickly, or it's very slippery and makes us fall behind the overall schedule. And so in real time, we'll also have to replan how to get from point A to say like a safe haven place where we need to be in order to survive the lunar night. So all kinds of interesting real-time factors come into traverse planning. Yes?
You talked about open source.
Yeah.
What are some ways that the students can, in a crowdsourced way, contribute to Viper and related programs?
Yeah, so that's a great question. NASA has long been trying to find ways to make it easier for others to take what NASA has done and use it for other purposes. That's one of the reasons why we release software open source. So you can take anything that we've engineered or knowledge that we've tried to encapsulate in terms of software and apply it to your own missions, whether that's a corporate mission and industry-based, or even an academic university-based missions. At Carnegie Mellon, for example, there have been a couple lunar rovers in development. One was IRIS, which flew and unfortunately didn't go anywhere because it was on a mission that didn't actually make it to the lunar surface. There's another mission rover developed at Carnegie Mellon called Moon Ranger, which we hope will still fly. I think beyond that, in terms of students contributing back, that's something that we're also still trying to figure out, well, what are effective ways of doing that? To engineer a system like Viper, for example, requires a lot of detailed understanding and knowledge about the lunar environment, which by and large, if you go to robotics departments across the country, very few of those have people who are experts in lunar surface, geomorphology and radiation and illumination conditions. And so I think we tend to focus more on those things where are more common to say terrestrial things, such as, well, what is the overall approach to say traverse planning? Motion planning is a good common thing. It's just about constraints and geometry. I'll say this not being a motion planner myself, and everybody else in the room who does motion planning will say, no, it's much more than that. But I think the key point here is that NASA doesn't exist to make profit, because we're a part of the U.S. government. We're funded by taxpayer dollars. Everything we do is meant to be disseminated, and open source happens to be one tool among many to do that.
So what if for example, what if students developed a machine learning model that developed digital elevation maps and then validated them in terms of quality or something like that? Would that be something useful for Viper?
Yes, it would be. And what we would do then is we would basically figure out, okay, do we have time to take a look at what's being done? How can we test that or verify its attributes like accuracy? And are there nonlinear errors across a particular map that is generated with a learning-based method versus a more traditional analytical method? The AIM stereo pipeline, for example, this open source set of tools here is very classic. It has a high quality, high fidelity, high accuracy stereo correlator at its core. And that feeds into basically a bundle adjustment approach where we take lots of different images and we bundle adjust all the different stereo observations. It's very traditional. There's no learning aspect at all to that. But because it's traditional, we can characterize its performance. We can understand the distribution of errors under different geometry conditions. And so that's why we rely upon that. If somebody's going to provide us with a learning-based system that produces similar outputs, we'll want to understand, okay, well, what are the limitations? What are the performance errors that might occur? And how do we basically combine those kind of things?
Okay.
Yep.
Thank you.
I think we're past time.
Yes, I think we're out of time, so we should thank Terry and